Howdy folks, and welcome to section 2.5. We're going to go over quadratic equations now that we've got the complex numbers to solve all of them, that is. Quick etymology, quad means four, like a quadcopter. A quadrangle is an obsolete word for a square. So quadratic just means an equation with a square in it, aka something like ax squared plus bx plus c equals 0, where a, b, and c are numbers. We're trying to solve for x. So these show up all over the place. They're in the spring equation, magnetism, gravity, acceleration, just all over the place. That's what I'm trying to say. It's a good kind of equation to know how to solve. They're very, very common. Now, we've gotten little sneak previews of this all unit because I've needed quadratic equations to do some of the examples in 2.3 and 2.4. But today's lesson is going to be entirely focused on these. So for example, if I say x squared minus x minus 12 equals 0, this is a quadratic equation. Most quadratic equations are going to have two solutions. If I graph y equals x squared minus x minus 12, the resulting graph looks like this. It's a parabola. They're boomerang shaped, and it crosses the x-axis and then comes back and crosses the x-axis again here. So we're looking for two different places where two different x values where the y value would be 0, where this whole thing would be 0. And so how we're going to find those, oops, have my mouse on the wrong screen. Here we go. We're looking for two different x values here and here where this whole thing would be equal to 0. How we're going to find those in this case is with factoring. Check this out. We know how to factor this. We need two numbers that add up to -1 and multiply to -12. So -4 and 3 will fit the bill. Having the factors of a polynomial is almost the same thing as knowing the roots. You can go from one to the other very quickly because of what we call the zero product property. Zero product property. I know I referred to this in yesterday's talk, but today we're going to get into what it means, or at least write it down in the notes explicitly. If I have two numbers, a and b, and I multiply them and get 0, there's no way to do that without one of the numbers being 0. I can't take two numbers that aren't 0 and multiply them and get 0. So either a equals 0 or b equals 0. And those numbers don't have to be written as numbers. It's anything with a numerical value, so any algebraic factor. So over here, if x minus 4 times x plus 3, these two factors, and they're factors because they're in parentheses and multiplied, if either of these factors is equal to 0, then my product will be 0. But if neither of these factors is 0, then the product won't be 0. So the only way to get this product of 0 when I multiply this factor by this factor is if one or the other of the factors is already equal to 0. So knowing this, I could say, so x minus 4, that factor is 0, or x plus 3, that factor is 0. One or the other has to be true. And then I can add 4 to both sides on the left here. X equals 4. Subtract 3 from both sides here. X equals -3. This is always going to happen, by the way. If you've noticed the pattern, this number and this number are additive opposites. They're negatives of each other. Same with this number and this number. And it has to be that way. You can see why it has to be that way by looking at the step in between them. I had to add 4 to both sides to go from this thing being equal to 0 to x being equal to 4. So that's always going to work with factors. So what that means on this graph here is that this is the point 4, 0. So x is equal to 4, and this whole expression is equal to 0. And this is the point, if x is -3, then the whole expression is equal to 0 again. So those are the two places where I can plug in those values of x and get 0. We can check that. 4 squared is 16, minus 4 is 12, minus 12 is 0. Negative 3 squared is positive 9, because the minuses cancel. Subtract a negative 3 and we get positive 12, and then subtract 12 and we get 0. So these are the two values of x that make this whole thing 0, just as advertised. But of course, we're not going to try to use guess and check to solve these. Factoring is a good way, though. So let's see here. Let's do another example. This will work even with trickier factoring problems. So maybe I want to know what numbers x can I have where 8x squared plus 2x equals 21. So I have some number. If I square it and multiply it by 8, and then I add 2 of the number, I'm supposed to get 21. Well, that's tricky. If we guess and check for a very long time, we might find out that, surprisingly, 1.5 works. 1.5 squared is 2.25. 8 times 2.25 is 18. 2 times 1.5 is 3. 18 plus 3 is 21. But my goodness, the amount of guessing and checking we'd have to do to realize that that was the answer. Not interested. So instead, I'm going to try to use the zero product property to solve. Now, this is the zero product property. If I know that I could factor this left side, check this out. I could factor this left side. I'm going to write this in red because it's correct, but it's not going to get us anywhere. So it fits all the rules of mathematics, but it's not skillful, if that makes sense. I could write this, well, 8x squared plus 2x equals 21. Factor out a greatest common factor of 2x. So 2x times 4x plus 1 equals 21. And like I said a moment ago, this is perfectly useless to us because there's no update. Come on. There we go. There's a little bit of a lag between when I actually write these things and when they show up. So this is perfectly useless to us. Useless. Because there's no such thing as a 21 product property. These two numbers could be 3 and 7, or they could be 1 and 21, or they could be the square root of 21 and the square root of 21 again, or any other combination of factors. There's infinitely many numbers. Like, check it yourself, 3 root 7 times root 7 would be 21. So how do I know what these two numbers are? This doesn't help us. So, but if I can make one side equal to 0 and then factor, then we're in good shape. So what I'll do is subtract 21 from each side and write 8x squared plus 2x minus 21 equals 0. Now, this is a lot better for us. This is a lot more useful, and that is a plus sign there. Because now if I can factor this thing on the left side, then I'll know that one of the two factors must be 0, and that'll get me my linear solutions. Bad news is that's kind of tricky to. So what I'm going to do is use slide and divide. I'm going to slide this 8 on down here. So x squared plus 2x. Oh, you know, I was writing these in blue in Unit 1, and I'm going to keep doing that. This is not the same as the polynomial we're trying to solve. This is a different one that's easier to solve. 8 times negative 21 is negative 162. I know, because 8 times 2 is 16, and 8 times 1 is... Oh boy. Oh boy. That's how this day is going to be, huh? 8 times 1 is 8, of course, not 2. Even math professors make silly mistakes sometimes, so don't beat yourself up for those. The important thing is to get the practice and know how things behave more than what the exact right answer is to every problem. Okay, so this is our easier problem, and 168 has a lot of factors. Well, I know it's got 21 and 8, but those aren't far enough apart. Let's make a factor tree of 168 so we can try to factor this, because I need two numbers that add up to 2 and multiply to 168. So like I just said, I know that 168 is 21 and 8, so that's 7, 3, and 3 2s. So I want to take these 5 prime factors and kind of put them in 2 buckets. So I could do 21 and 8, but those aren't 2 apart. I need to split these into 2 numbers that are 2 apart. How about 6? 3 times 2 is 6. And then 7 times 2 times 2 is 28. No, that's even worse. Okay, how about 12 and 4? Oh, 12 and 14. 7 times 2 is 14. And then, so that's these numbers. And then check this out. 3 times 2 times 2 is 12. And those really are 2 apart, which is what I want. And so I know 168 has to be 14 times 12 because I used all the factors. So 14 times 12, well, 12 times 12 is 144, so 2 more 12s is 24. 144 plus 24 is 168, so this is what we want. 14 and 12, that means I can factor this guy as x plus 14, x minus 12. You see why having them be 2 apart is what I wanted? This is negative. 14x minus 12x does get me this 2x, so. Now, this doesn't mean our roots are 14 and 12. Remember, this blue polynomial is the easy one. Now I need to slide back. So I need to divide both sides by 8. Or both sides. I need to divide both of these guys by 8. So I'm going to get x plus 7/4 and x minus 3/2. And to finish, we're going to slide those denominators back up. So I'll call this one 4x plus 7 and call this one 2x minus 3. Should have written that in black. Let me fix that real quick because these are the factors of the original problem now. There we go. So those are the factors of the original problem. Once you slide back, and you can check if you FOIL 4x plus 7 times 2x minus 3, you really do get 8x squared plus 2x minus 21. So then, the factoring's done. So this blue work was slide and divide. You can also use something called factor by grouping. Wow, why couldn't I remember that? You can also use something called factor by grouping, which is in your textbook. Personally, I like slide and divide better, but either one. Let's see what roots we get from these factors. This means by the zero product property, either 4x plus 7 is 0 or 2x minus 3 is 0. So over here, I'm going to subtract 7 from each side and then divide by 4. Over here, I'm going to add 3 to both sides and then divide by 2. So my roots are 7/4 or positive 3/2, negative 7/4 or positive 3/2. Sorry there. My nose was right on the boundary between sneezing and not sneezing, and I think it's not going to sneeze, but that's why I paused there. You could plug these back into the original equation all the way back up in the first line if you want to make double sure, but these really are the correct solution, so I'm not going to do that. And check out the pattern. This number, but opposite, is the numerator, so 7 becomes negative 7, and this number is the denominator, 1/4. This number, but opposite, positive 3, divided by this number, 2. So that's how you go from a factor like this to your root. These are the most complicated kind of factors you can get. It's always going to be linear, so it's always going to be mx plus b in here, right? But that's how you go from the most complicated kind of linear factor to a root. So we've got our zeros. Okay. Well, let's do one more of these. If I said x squared minus 9x equals 0, what I'm going to factor out here is the greatest common factor. So x times x minus 9 equals 0, because x times x is x squared, and x times negative 9 is the negative 9x. Over here, we can see from the pattern from before, that's going to be the root x equals 9. But people always get confused for some reason. What root do I get from the x? I don't know why, but a lot of our instinct says to say 1. In math, it's not always a good idea to trust our instincts, because going from the zero product property, this one would say x minus 9 equals 0. Add 9 to both sides. That's how we get x equals 9. But what would this one say? It would say x equals 0. And we don't have to do anything to each side. It's already solved. Our solution here is x equals 0. So in this equation, either x equals 0 or x equals 9. When you get the simplest possible factor, an x by itself, or its friend x squared or x cubed by itself, same thing really, that's a root of 0. Okay. So sometimes quadratic formulas are actually, or quadratic equations rather, are actually easier to solve. There's something that can be really helpful to us. Remember that our general form is ax squared plus bx plus c. I want to talk now about the case where there's no bx. If that doesn't show up and you just have ax squared plus c, we're in kind of an easier case. So if I said, for example, x squared minus 7d equals 11, the thing that makes quadratics hard, the reason I have to use these special methods instead of doing something so much easier is when we're trying for x, we're trying to get x by itself. And the fact that here x is squared, but right next to it here x is to the first power, and then there's a constant term as well, makes it very difficult to isolate x. You could try playing around with these on your own. This is what not to do is, if I try to play around with these on my own, like try add 21 to each side, subtract 2x from each side. You're just playing a shell game, shuffling things back and forth between the left and the right. No amount of adding or subtracting is going to be able to change these two different terms. These are not like terms, x squared and x. No amount of adding and subtracting, shuffling terms back and forth is going to be able to isolate x without factoring or some other advanced method. But over here, there's no linear term, and so shuffling things back and forth is actually really good. I'm going to add 70 to each side. So now I've got the x squared by itself. And x squared is the only term with an x in it, so the x's essentially are by themselves, and all I have to do is get rid of this squared. I think you know what the square root of 81 is. You'd be tempted to say the answer is just x equals 9, yeah? But that's almost correct. That's very close to correct. The answer in this problem is x is positive 9 or negative 9, and we're going to write that like this, plus or minus 9. So this symbol means the solution is plus 9 or minus 9. That's what a plus or minus symbol means. And the reason for that is that 9 squared is 81, of course, but negative 9 squared, negative 9 times negative 9, first thing that happens is those minus signs cancel out, and we get positive 81. So there are two solutions, plus or minus 9. I think your textbook calls this the square root property. If there's no linear term, we can isolate the x squared and then take the square root, slap on a plus or minus. So if this had been x squared equals 16, the answer would be plus or minus 4. Here's a more complicated example. X squared plus 8x plus 40 equals 4 times 2x plus 1. Not knowing anything going into this problem, my goal is going to be try to get one side equal to 0. So I'm going to try to simplify the right-hand side. I'll distribute the 4. And then I'll try to move everything from the right side to the left side so that the right side has nothing on it. So I've distributed the 4 to the 2x and the 1. And now I'm going to subtract 8x from each side and then subtract 4 from each side. So when I subtract the 8x's, well, they actually cancel out of the left-hand side. And then subtract the 4's. Now I told you back in chapter 1, sum of squares does not factor. There's no way to factor x squared plus 36. So our only way forward, the only thing we can do is to try to use that square root property. Since there's no linear term, I'm going to subtract 36 from each side. And now it's very handy that we talked about complex numbers yesterday because that's the solution here. The square root of negative 36 is the same as the square root of positive 36 times the square root of negative 1. Okay? So that is 6 times I. So my answer here, x squared equals negative 36. That means x equals not just 6i, it could be positive 6i or negative 6i. We're all going to do this plus or minus thing here. And the reason for that is positive 6i squared equals 6 squared times I squared. That's 36 times negative 1, so that's negative 36. Negative 6i squared is negative 1 squared times 6 squared times I squared. Negative 1 squared is just 1, so this is also negative 36. So we have two solutions here, plus or minus 6i. So this is our first example of complex numbers being the solutions of a quadratic problem. This square root property, counterintuitively, it can actually help us out even in situations where there is a linear term. And let me introduce this kind of gently here. I'm going to do 3 examples in a row that show sort of advanced applications of this square root property. And here's the first one. Imagine I said x minus 2, all in parentheses squared, equals 25. Now, of course, one way to solve this would be to FOIL the left-hand side. So x squared minus 4x plus 4 equals 25. Then get the right side equal to 0. X squared minus 4x minus 21 equals 0. So I subtracted the 25 away to get nothing left but 0 on that side. And then we can factor x minus 7 times x plus 3 equals 0. So x equals 7 or x equals negative 3. That's one way to solve the problem. But as a matter of fact, it's not the only way. The other way is actually, the way I'm about to show you with the square root property is a lot simpler. See, the square root property just says that, come now, like this. The square root property just says that, let me write it up here. If k squared equals a, then k equals positive or negative the square root of a. That's what the square root property itself says. So you can see how that's used in this method here. If x squared is negative 36, then x, okay, is positive or negative the square root of negative 36. So here, instead of k being x, here k is this whole expression, x minus 2 squared. If this thing in parentheses squared is 25, then this thing by itself is plus or minus the square root of 25. So we know that that's positive or negative 5. So I know that x minus 2 equals positive 5, or x minus 2 equals negative 5, which means that x equals 7, or x equals negative 3. Add 2 to both sides. So this is a little bit quicker of a way to get this same answer than this method over here. Since we have, so this quadratic equation, if we simplify it and get it into standard form, it's got a quadratic term and a linear term. But over here, those were grouped into a perfect square. So if you have a perfect square, oops, don't want to write that in black. So we have a perfect square right here, and that allows us to use the square root property. The only term with x in it is inside a perfect square already, and so we can take advantage of that. So here's a little bit more complicated. Let's say that our problem was 3 times x minus 4 squared minus 5 equals 0. Now, if I simplify that out, that's going to be 3 times x squared minus 8x plus 16 minus 5 equals 0. That would be 3x squared minus 24x plus 43 equals 0. And that's a particularly nasty slide and divide problem. And so I'm not going to solve this way. That's as far as I'm going to go, because rather than solve a particularly nasty slide and divide problem, I could solve a relatively easy perfect square problem. I'm going to get the perfect square by itself. So I'll add 5 to each side. And then I'm going to divide each side by 3. And now instead of a particularly nasty slide and divide problem, which as a matter of fact I'm realizing now is unsolvable, instead I can take the square root property and add 4 to each side. X is 4 plus the square root of 5/3 or 4 minus the square root of 5/3. We were never going to be able to factor this because the solution has a radical in it. So this is this square root property is the only way I've shown you so far that would actually work. So how can we use that if we're not handed a perfect square? The answer is to try to produce the square ourselves. So this process is called completing the square. We're not given the perfect square. We're going to try to make it ourselves. So let's say I was told that x squared plus 4x minus 7 equals 0. I will tell you right now, there's definitely no way to factor this. You can check that yourself. What two numbers multiply to -7 but add up to positive 4? There's the sneeze. Okay, only 20 minutes late. What two numbers multiply to -7 and add up to 4? I challenge you to think of them. I know I can't. I even have them written on my page here. It's -2 plus root 11 and -2 minus root 11. I would not come up with those, and neither should you. So instead, what I'm going to say is, if I had a perfect square here, I want you to think of it this way. If you had a perfect square here, what would it look like? It would start with, it has to include the x squared plus 4x, and then something else. X squared plus 4x is x times x plus 4. That's not a perfect square, but if you've played with polynomials enough, you might recognize where we're going with this. What's a square expression? X squared plus 4x plus blank. Well, I could say, I know from playing with polynomials a whole lot, I know that x plus 2 squared is x squared plus 4x plus 4. Because outside and inside are 2x and 2x, and last is 2 times 2 is 4. In fact, that's probably worth writing down. This is x plus 2 times x plus 2 is first x squared, outside 2x, inside 2x, last 2 times 2, 4. So I know if I had x squared plus 4x plus 4, I would have a perfect square. But I've got x squared plus 4x minus 7. So I want to pretend like I have this perfect square here. I want to pretend, and I'll show you how to get this number every time in a bit, but I want to pretend like I have a perfect square here. So what I'm going to do, and this is a little weird, is I'm going to say, okay, x squared plus 4x plus 4 is what I want, but I don't actually have that 4, so I'm going to get rid of it. I don't have that 4, so I will subtract, update. There we go. The lag on this screen is unreal. I'm going to write plus 4 minus 7. So I haven't changed the value or anything. Do you see? I've added 4 and subtracted 4. Those cancel out. So this is just equal to x squared plus 4x minus 7. I haven't changed the value of the equation. But what I've done is said, I've written out my perfect square. Christ. iPad's acting up. This is x plus 2 squared minus 4 minus 7 is -11. So now I have this expression. And now I can use the perfect square property. I'll move the 11 over to the right. I'll take the square root property, and I'll subtract the 2. So my two roots are -2 plus the square root of 11 and -2 minus the square root of 11. There we go. Yeah, it's slow today. Peak internet hours or something. Should record these early in the morning instead. But yeah, so we've got our solutions. And if you want, you can plug these in and check, but that doesn't sound very fun to me. How that would look is something like, okay, -2 plus root 11 squared plus 4, -2 plus root 11 minus 7 equals 0. I'm only going to do this once just to justify that this method really works, even though it feels pretty magical. Foiling the first expression, you could do this at home. 4 minus 4 root 11 plus 11. So first, outside, inside, and last. Distribute, -8 plus 4 root 11 minus 7. Okay, first things first, these terms cancel, and then 4 plus 11 minus 8 minus 7. Someone's done something wrong, and it's me. Oh, wow. Okay, yeah, that's 4 plus 11 is 15, minus 8 minus 7 that really is 0. Okay. Took me a second to see it there. I don't know. Okay. I don't even know what I was thinking. Yeah, that really is 0. 4 plus 11 is 15, minus 8 is 7, minus 7 is 0. So I'm just going to do that for the one solution. You can check at home if you want that if you put a minus sign here instead of a plus, you'll get the same thing, 0. But yeah, these really are the roots of this polynomial. So this is just to check. You don't have to do this every time or even ever at all. So let's try another one because, again, this is much easier to see by practice. If I said x squared plus 6x plus 5 equals 0, now I know you already know this is x plus 2 times x plus 3, but I'm going to try to do it with completing the square. Okay? So I know that you know that we can factor this as x plus 2 times x plus 3, so the roots should be -2 and -3. You could even plug them in and check. They really do work. But what I'm going to say is, if I had a perfect square, x squared plus 6x plus something, what would that be? It would be x plus a number times x plus a number. And that number, remember, these two numbers, this one and this one, they have to add up to 6 and multiply to whatever this is. Well, now, if they add up to 6 and they're both the same number, then they've got to be 3 and 3. And so they must multiply to 9. So half of the 6 goes here, and half of the 6 goes here. That's how to find this number. It's half of the 6. X plus 3 times x plus 3 must be x squared plus 6x plus 9. So I want this to say x squared plus 6x plus 9. And what I'm going to do to make that happen is x squared plus 6x plus 9 minus 9 plus 5 equals 0. See, I haven't changed the value, but now I have, this is a perfect square, and this is, looks like -4 this time. So this is x plus 3 squared minus 4 equals 0. X plus 3 squared, move that over, is 4. Use my square root property. X plus 3 equals plus or minus, and the square root of 4 is 2. Like so. Subtract the 3. X equals -3 plus or minus 2. That is a weird way to write the solution. I can spread this out. This is x equals -3 plus 2 or -3 minus 2. So this is -3 plus 2 is -1, -3 minus 2 is -5. And those really are our solutions. If I plug those back in up top, -1 squared is 1. This is -6 plus 5 is 0. With a -5, it would be +25 minus 30 plus 5 really equals 0. I realize now that at the beginning of this problem, I said the wrong thing. At the beginning of this problem, I said something to the effect of x plus 2 times x plus 3. That would be x squared plus 5x plus 6. So I had that backwards. This is x plus 1 times x plus 5, of course. So my bad. If you caught that at home and you've been yelling at your screen the whole time I was solving the problem, now you're vindicated. Very good. You're smarter than me. But see, that's how complete the square works. So if I had x squared minus 8x plus 7 equals 0. Again, I think this is one that factors. I think this factors into x minus 1 times x minus 7. So our solutions should be 1 and 7, but doing it the other way, complete the square, I'd say x squared minus 8x plus what? Well, I know x squared minus 8x. I'm going to have to make that into x minus 4 times x minus 4. Because -4 and -4 are the two numbers that are the same and add up to 8. They have to be the same because I want a square. They have to add up to -8 because that's how factoring works. So their product is going to be 16. X minus 4 times x minus 4. The perfect square is x squared minus 8x plus 16. So over here I'm going to write, whoops, don't need parentheses yet, x squared minus 8x plus 16 minus 16 plus 7 equals 0. So this is x minus 4 squared. This is -9. So x minus 4 squared equals 9. Use the square root property and say x minus 4 equals plus 3 or minus 3. So x equals 4 plus 3 or 4 minus 3. X equals 7 or 1, like I said. This even works. This even works when here we go. Here we go. Lost my place in my notes now, didn't I? This even works for problems that can't normally be factored. So let me go back and say again, let's say x squared minus 8x plus 1 equals 0. There's no way to factor this. I can't think of two numbers that add up to -8 and multiply to 1. That would be a tall order. But what I can say is, just like before, I would love it if I had the perfect square, x squared minus 8x plus 16. And the way to do that is to add and subtract 16 in the middle here to say, okay, well, these three terms are x minus 4 squared, and then this is minus 15 equals 0. X minus 4 squared equals 15. Square root property says x minus 4 equals plus or minus the square root of 15. So x equals 4 plus or minus the square root of 15. So that's a number just a tiny bit bigger than 0. 4 minus the square root of 15, because 4 is the square root of 16. So 4 minus root 15 is going to be between 0 and 1. 4 plus root 15 is going to be between 7 and 8. So there's our two roots. There was no other way we've seen before to get this answer. Now, complete the square gets ugly fast is the problem. If I were given numbers that suck, like x squared plus 3x plus, what's going to suck? X squared plus 3x plus 4. Okay, this doesn't have any factoring solutions. It has solutions, it has two of them, but factoring isn't going to get us. It's the other way around. X squared plus 4x plus 3 is easy to factor. This one's impossible to factor because I can't have two numbers that add up to 3 and multiply to 4. Just don't work like that. So I want a perfect square, and here's where complete the square gets sucky fast, is x squared plus 3x plus what? Oh, bother. Oh, bother. See, the two numbers, right? They have to add up to 3 and be the same number. And sadly, that number is going to be 3 halves. Two of the same number that add up to 3. What else could it be but half of 3? 3 halves times 3 halves is 9/4. Just multiply the top and bottom, right? So this is where things get crummy. What I'm going to do is write x squared plus 3x plus 9/4 minus 9/4 plus 4 equals 0. Now, these three terms are x plus 3/2 squared. These two terms, I don't know if we've done this yet this semester. -9/4 plus 4 is the same as -9/4 plus 16/4. Get a common denominator. So this is plus 7/4 equals 0. Oh, bother. And then things go from bad to worse. We have to subtract the 7/4. X plus 3/2 squared equals -7/4. Now we'll use the square root property. Oh, bother. X plus 3/2 is either negative the root of -7/4. Well, boy howdy, it's a good thing we know how to take the square roots of negative numbers now, isn't it? That's the same as plus or minus √7 divided by 2i. So I split up the fraction, right? There's a property that says root -7/4 is really the same as √7 √-1 divided by √4. That's what I'm doing here. So √7 came right over. √-1 is our I. √4 in the denominator is just 2. And now I can subtract 3/2. So x is either one of these complex numbers, -3/2 plus √7 over 2i, or -3/2 minus √7 over 2i. If there's an uglier pair of numbers, I don't think I've seen them. These are our solutions, though. So complete the square got ugly fast. If the leading coefficient isn't 1, it gets even worse. So what I'd like to do here, let's do an example. Let's say I have 2x squared plus 10x, I don't know, minus 17 equals 0. Here's what I'm going to do. I'm going to pull the 2 out of these first two terms, because I don't like factoring with leading terms. I'm going to write 2 times x squared plus 5x. So this is a weird kind of half factoring, right? But you see, each of these terms had a 2 in it, so I pulled it out. Now, I know I want a perfect square here. So what I'm going to say is x squared plus 5x plus what? Well, sadly, we're in crap situation again. X squared plus 5x, well, it's going to be x plus something, x plus something, and I'm sad to inform you that that something must be 5/2 because it's half of 5. 5/2 plus 5/2 adds up to 5, and it multiplies to 25/4. Oh dear. Plus 25/4 minus 25/4 minus 17 equals 0. This is the worst case scenario for complete the square. What I have to do is distribute the 2, and this is weird as well, to this thing and this thing. So I'm going to say 2x squared plus 5x plus 25/4 minus 25/2, 2 times 25/4, minus 17 equals 0. 17 is 34/2. So altogether, I've got 59 halves over here, 59 halves. And I'm going to just divide both sides by 2 right now and make 59/4. So I get that x plus 5/2 squared equals 59/4, and x is -5/2 plus or minus √59/4. Terrible, just terrible. So I'm not going to recommend you use complete the square in this situation. What I'm going to do is some kind of ultimate one-for-all sacrifice right here, just so that we never have to use complete the square again if we don't want to. Now, it was really handy in a couple of those problems up above, but down below it's got so complicated that I hate it. What I'm gonna do, and you don't have to replicate this, but I like it. ax squared plus bx plus c equals 0. I'm going to complete the square with the a, b, and c placeholders still in. I'm going to complete the square. And whatever we get for that solution is going to get us there. Now, I'll go fast, and feel free to fast forward if you don't want to follow through this, because it is mind-bogglingly dense algebra, but just for the sake of seeing it. So I don't want this leading coefficient. I'm going to divide both sides by a. The thing I'm going to add and subtract, I have x squared plus b over a x plus something. So the thing I add and subtract is b over 2a. Has to be, because it's half of b over a. Yeah. So I'm going to write this. Whoops. That should be a b. Plus b over 2a minus b over 2a. Oh, nope. The thing I didn't subtract is b over 2. Sorry. This number in here is b over 2a. When I square that, I get b squared over 2a squared. So 4a squared, because 2a times 2a is 4a squared. So the thing I'm going to add and subtract is b squared over 4a squared. So then these first three terms are x plus b over 2a squared. And the last two terms, well, what I'm going to do is say c over a, multiply the top and bottom by 4a, is the same as 4ac over 4a squared. That way I have a common denominator. So what I've got is 4ac minus b squared over 4a squared. I'll move that to the other side. B squared minus 4ac. Geez, where have I heard that expression before? B squared minus 4ac. I swear that is something. Now we'll take the square root property. Oh, plus or minus the square root of b squared minus 4ac over 4a squared. Whoops, 4ac. What I'm going to do here, remember the square root of top over bottom is the same as the square root of the top over the square root of the bottom. Well, this bottom here, 4a squared, the square root of that is 2a. So I'm going to rewrite this right now as plus or minus root b squared minus 4ac over root 4a squared, which is 2a. So now all I have to do is subtract this negative, where's my cursor? Subtract this b over 2a. And so x equals negative b over 2a plus or minus root b squared minus 4ac over 2a. And since I have a common denominator, I might as well combine them. X equals negative b plus or minus root b squared minus 4ac over 2a. Just for those of you who didn't want to follow that. If you were fast forwarding through that, it would be a good time to stop fast forwarding right around now. Okay, and now that we're all back with us, what did I get? This right here is the quadratic formula. So that is where the quadratic formula actually comes from, is someone with a lot of patience, like I just did, sat down and completed the square without plugging numbers into the quadratic equation, and they got the quadratic formula out of it. So these are the two values of x in terms of a, b, and c that'll make things work. So now, instead of having to do this awful business up here, scroll up here, 2x squared plus 10x minus 17 equals 0. Instead, I can say, if 2x squared plus 10x minus 17 equals 0, Fresca was feeling a little parched there, then A is 2, B is 10, C is negative 17. X equals negative B, so negative 10, plus or minus root B squared, 100, minus 4AC, so negative 4 times 2 times, oh boy, negative 4 times 2 times negative 17. Jeepers creepers, that's 28, 68, 68 times 2, 136. So plus 136 all over 2a, all over 4. And those are our solutions. Well, we could simplify this a little bit. 236 is what's under the square root there. I put a plus here because the minus is canceled out. Sorry, I put a plus here because these minuses canceled out. 236, 118 times 2, that's 59 times 2 times 2. Okay. So this is negative 10 plus or minus 2 root 59 over 4. And then we can cut out a factor of 4. It's negative 5 halves plus or minus root 59 over 2, which is the same answer we got up above, but this was a lot quicker. We didn't have to do all that horrible complete the square arithmetic. It's only horrible when you have bad numbers for it. When you have good numbers for it, it's a lot faster than the quadratic equation. But the really cool thing about the quadratic equation is that it works on every problem. No matter how simple or how hard, it'll work on every quadratic. The quadratic formula will work on every solve this equation with x squared in it. By the way, this b squared minus 4ac over this b squared minus 4ac under the square root, there's something special about it, and I want to do 3 more examples to showcase what's special about it. There we go. All right, what's special about it? Suppose I had x squared minus 10x. Uh-oh. Uh-oh. Okay, we're back. My screen just went black and I don't know why. Suppose I had x squared minus 10x plus 21 equals 0. Now, you can factor this. You can factor this into x minus 3 times x minus 7. So our roots are going to be 3 and 7. If I graph this thing, in fact, here are our roots, 3, 0, and 7, 0. But I said the quadratic formula works on every problem, no matter how simple or how complicated. So a equals 1, b equals negative 10, c equals 21. Let's get started. X equals negative b, so positive 10 is negative b, plus or minus root b squared, 100, minus 4ac, minus 84, all over 2a. So x equals 10 plus or minus 16 over 2. That's 10 plus or minus 4 over 2. So that's 6 over 2 or 14 over 2. That's 3 or 7. Just like you could see from factoring, those are our 2 roots. Here, what happened is 10 over 2, if I didn't add or subtract anything, well, heck, let's do that and then I'll compare. What if I didn't add or subtract anything? What if I had x squared minus 10x plus 25 equals 0? Plus 25 equals 0? One moment. Okay. Then x would be equal to plus 10 plus or minus root 100 minus 4ac. So minus 4 times 1 times 25 is 100 over 2. So that's just 10 plus or minus 0 over 2 is 5. The graph here, the parabola just touches at 5, 0. So let's compare these two situations. Up here, the number under the square root I call the discriminant, and I'll tell you why in a minute. Here, the number under the square root is 16, so d is 16. It's a positive number, so I'm going to start at 10 halves, start at 5, 0, and I could go up by 4 halves, up by 2, or down by 2. So the quadratic formula is saying start at 5 and go up 2 to 7, or down 2 to 3. Here it's saying start at 5 and don't go up or down anything at all. Go up or down by 0, and there you are. So this parabola, the only difference is I moved it upward 4 units. I added 4 to the equation. And so this thing lifts up 4, and now just the very tip is on the x-axis. So if the discriminant is positive, we can go left or right and get 2 roots. If the discriminant is 0, we're not going to go left or right at all. We're going to have the same root twice. And now what if the discriminant is negative? I need to think of an example. Should have done this before I recorded. Pay no mind. Give me one moment. 30. Okay. What if I move this up further and I say, third example, x squared minus 10x plus 34 equals 0. So now we're in a situation where on the graph, I've moved this up another 9 units. And so the parabola, rather than touching at 2 points or touching at 1 point, it doesn't touch at all. There are still 2 roots, but they're both going to be complex numbers because they're not on the real number line. They're going to be lost somewhere in space on this diagram. Well, let me quadratic formula. X is negative b, so positive 10, plus or minus root b squared, 100, minus 4ac, so minus 4 times 1 times 34. That's 136. All divided by 2a. 2 times 1 is 2. So now our discriminant is negative. Our discriminant is 10 plus or minus root negative 36 over 2. Well, you know what? So we've got a negative discriminant. We don't have any real roots. We have 2 complex roots. Let's find them. So 10 halves is 5 plus or minus root negative 36 is 6i. So this is 5 plus or minus 3i. Our roots are 5 plus 3i or 5 minus 3i. Whoops. Cool fact. Did you notice these are complex conjugates? In fact, every time I've gotten complex roots, they've been complex conjugates in this section. That always happens. 5 plus 3i or 5 minus 3i. The real part's the same. The complex part is just switched. That always happens. We'll learn more about that. It's called the conjugate zeros theorem. We'll learn more about that in Unit 3, but that always happens when you've got a regular quadratic expression. You can see why from the formula, but okay. The moral of this story is, if your discriminant is positive, scroll. Oh my God, scroll. There we go. If your discriminant is positive, you'll have 2 real roots. If your discriminant is 0, you'll have 1 real root. And discriminant is negative, then you won't have any real roots. So when I was looking at, let's say, this awful problem here, x squared plus 3x plus 4. Before I even started the problem, if I just wanted to know whether there were any real solutions, it'd be very simple to find out. I'd say the discriminant is b squared minus 4ac. In this case, that's 3 squared minus 4 times 1 times 4. So the discriminant is 9 minus 16 is negative 7. Since this is negative, there are no real roots. And indeed, we find out that both of the solutions are these complex numbers. So that's how the discriminant helps. Helps us see whether we're going to get good solutions or not really quickly. All right. That's all for 2.5. Join me next time for a section imaginatively titled More Equations. So long for now.